Yeah, okay, good save. At time equals 1, where are we?
We're at 1. When t equals 1, we're at 1, 1.
Okay, when t equals 1, we're at 1, 1. When t equals 2, where are we?
2.
2 is a number, not
2,
a place.
2, 2.
2, 2. So does that cover the entire curve?
No.
So where does t needs to range to cover the entire curve?
1 to 3.
1 to 3 sounds reasonable. So in this parameterization, we decided to have t go from 1 to 3 and not start at 0. We can pick t to go from whatever initial starting point and ending point I like. Okay, it's our choice of parameterization. So I got a parameterization. Let's compute this line integral. ds. Let's look at Nasser. How do I finish this line integral? Tell me what to write down here.
I'm just still writing. We do like what, integral 1 to 3, and then we just put our, would x be t plus?
Just tell me exactly what to write down here.
So t plus t minus 1 squared plus 1, and be dt.
dt. What are we missing here? We evaluate the function. What else do we need? We need our length term, right? We're integrating with respect to arc length. So how do we organize arc length with respect to t?
Square root dt or dx dt squared.
Yep, which is?
1 plus
t plus t minus 1 squared plus 1, square root of 1 plus dy dt. Two times t minus 1 dt. Okay. And then you evaluate.
Wait.
Questions?
I have a question.
Yep.
The first part, the t plus t minus 1 squared plus 1, that's our parameterization of our function and the integral that we're given.
That's our function evaluated on the curve that we're interested in. Right. So this is f of x of t, y of t.
Yeah. Okay.
Right. We're integrating our function only on the curve. So this restricts our function to the curve. Okay. So,
did you see Maggie's question on chat?
Yep, I just saw it there. How do you parameterize? We should parameterize well. That's how we should do it. So please, like I said this last time, please look back at the previous section on parameterization. It's chapter 13. I'll say this one more time. Look back at parameterization on chapter 13. It is really important as we move into chapter 16. Okay? We will need to know how to parameterize things. Planes, lines, curves, surfaces. Okay? So be good at parameterizing things. Okay. So last time we talked about line integrals and over curves that weren't necessarily smooth. So we chopped it up into nice smooth bits and added up the line integrals, right? So the picture has the book has a nice picture about what a line integral could mean geometrically. I'm going to attempt to replicate it because I wanted to draw some other stuff that the book doesn't talk about. So if the picture looks shitty, sorry. And just a heads up, it probably will look shitty. So let's imagine C is a curve in 2 space. It's this curve. Okay, I left some spots out here. Imagine these are connected. I left this out for a reason. Okay, this is C. And I have a function f. This is f. Yes. Right, so the height of my function depends on where it is at the curve. Pretty straightforward, right? So this, again, this picture is in the book, but the line integral ds can be interpreted as this shaded region, the red stuff. Okay, it's the area of that region. Okay, that is a geometric way to interpret this line integral. But in practice, this only really makes geometric sense when f is a function that describes this height, right? If f is something like density, then this picture doesn't really apply. But we can think of a line integral like this. Okay, does that make sense? This is nothing new. This is just a picture in the book. And admittedly, that's pretty good. One of my better pictures. Okay. Any questions about this picture? No. So why did I care about this? Because there are 2 things that we could integrate with respect to here. I guess 3. The one that we chose is arc length. So that means I took blue pen. Gotta find a blue pen. I chopped up the curve in terms of the arc length. So I chopped up little bits of the curve like this, right? And this is my differential. But I could also chop up the plane or the sections of the curve like this, right? So now instead of following along the arc, I move along the x-axis, right? Or the y-axis. So I have a couple of vantage points or ways to chop up my curve, right? So it makes sense that I should be able to compute these integrals as well. right? We're gonna write that down. So it says we can replace ds with dx or dy or dy. This is saying chop up the curve with respect to a different variable. Right. So we computed this integral here. We can also compute this integral. Dx or integral c f of x dy. It's exactly what we just described. Instead of chopping up along the length, we're going to chop up parallel to the x-axis or parallel to the y-axis. Okay? So what does this mean geometrically? I'm going to attempt to draw this picture. So the book doesn't have a nice picture here, so I'm tasked to make my own. So since I'm only really moving, let's look at x. X is going to be easier to draw here. Along the x-axis, right? I'm chopping up little bits of this curve and adding up the height, right? So I can think of this integral here as a projection of this object onto the x-axis, right? So imagine if I was standing right here and I shine a flashlight at this little wall thing. What outline would I get on the x-axis? I'd get something like this. Okay, let's try to draw this. Right? And all of this is shaded because there's a screen right there that's covered by the height. So this integral right here represents this area. Right? If I were to do the same thing for y, it would look a little harder because this picture is kind of in the way. And it goes a little back and forth. So there's some cutting in between. So it'd be something like this. Okay. Does that make sense?
Would it be a function for y since it's got more than one point of intersection?
It wouldn't be a function because this is a number, but it would the picture, well, you've hit the nail on the head there, I guess. This projection, if I was standing here and I shine it over here, I'd see just one thing that doesn't capture this curve going back and forth, right? Because I wouldn't be able to see that from the front side. Okay, so the weaving back and forth in the y direction is not captured by this projection. It's captured in this integral by having some negative points and some positive points and things like that, but not in this picture. Does that make sense? Okay. But delta S is the only one you will evenly distribute chunks. But delta S is the only one that will give you evenly distributed chunks. No, Maggie, I can make, see, think about this. I have control over the size of this length and this chunks and these chunks, right? I have complete control over how big delta S is, delta X is, or delta Y is. They can be different, yes. But in the end, when I make them small, they're going to go to the same value, right? They're all going to be small, right? So they can start being different, but eventually when the number of blocks I split this curve into gets big, the chunks will all be really small in size. Okay. Does that make sense? This is not a, the book didn't describe, this book didn't have a nice picture here, but this is what you should think about when you think about these kinds of line integrals. Okay, so now I want to compute these line integrals. And there's a nice formula for these, just like you'd expect. So recall, integral over c of f of x, y, ds, the dyslexia there, this is equal to the integral from a to b of f of x of t, y of t, square root x prime of t squared plus y prime of t squared dt. Right? Exact same equation that we just used. So now let's think about how I would compute this if I wasn't worrying about how the y changes, right? Because in this picture, if I'm computing this quantity, I don't care about y, right? I've done a projection on x. So it should, if I did this computation, look exactly like we expect. The integral from a to b of, I'm still evaluating my function, but now the y changes don't mean anything. They're zero, essentially, right? So I should just get the square root of x prime squared, right? Which is just x prime of t dt.
That's because you integrated with respect to dx?
Because I'm integrating with respect to dx, exactly. And similarly, integral f of x, y, dy is integral ab y prime t dt. Okay. So nothing extremely new. I mean, it's a new quantity, but we compute them exactly the same way. We parameterize it, we evaluate the function on the curve and multiply by its derivative. Okay, any questions? No. A little bit of notation, which I think is absolutely horrible, but it's necessary because it's always discussed. So if I have two integrals, c p of x, y dx, over the same curve is important here, q of x, y dy, where p and q are continuous functions. Sometimes, this is to save space, this is written like this, with one integral over the same curve, p of x, y dx, q of x, y dy. Okay, so I want to be clear about what this means. So previously, our discussions of integration, we added two integrals when they were integrating with respect to the same variable, right? So this is clearly not the same variable, okay? This is something different. We're integrating over the same curve with respect to these different variables. But I want to say they're actually kind of the same. And how are they kind of the same? We parameterize x and y in terms of some variable t. Okay? So this grouping into one integral is with the understanding that x and y are parameterized by the same variable. This grouping. Wait a second. This grouping is with the understanding that X and Y are parameterized by the same variable. Okay? So if we're going to compute this integral, that literally means parameterize X and Y in terms of one variable, and then we can add those integrals together. Okay? Does that make sense?
I have a question.
Mhm.
Could you explain to me why, when it comes to dx and dy again, that we're stuck with just x prime of t dt and y prime of t dt?
So there's two reasons here. The first reason, I guess they're not really in any order, but the first reason I'll talk about is if you go back to the derivation of this line integral, when you got this whole thing because of this was the arc length, the derivative of the arc length, right? So if you went back and did the derivation, you would get this is the derivative of the arc length. But I'm not integrating over arc length. I'm just integrating over the x coordinates. So if you did the exact same thing, the same formulation, you would get just x prime. Right?
Okay.
So that's the mechanical reason. If you go back and actually follow the computation through, that's what will come out.
All
but
right.
A more sort of heuristic reason is because I'm focused on this integral here only on x, right? So changes in my y are insignificant. They don't affect my integral at all, right? If I'm integrating over just x, like in this picture, I'm stuck here. Moving this way doesn't matter, right? So my derivative y primes really should be 0 with respect to this integration, right?
Yeah.
And consequently, if y prime is 0 here, this is 0. We get square root of x of t, x prime t squared.
Okay,
So
yeah, that makes sense.
So those are two really the same thing. They describe the same thing. One is a heuristic reason why it works, and then the other, which I didn't actually detail, is the technical reason why it works. So if you went through the computation, you get the same answer.
Could you also phrase it as you're holding y constant while you integrate with respect to dx? And you hold
Yeah, I mean,
yeah.
yes, you can phrase it as y is being constant, and in essence, its derivative is 0, right? Yeah, you really could do that because you're making a projection onto the x-axis, essentially, right?
So by doing this, by focusing just on the x-axis and the y-axis separately, you combine those two, like.
Well, yes and no. You don't combine them in the same way that you think to make arc length.
Yeah.
Okay, but we will use the combination of this when we talk about vector fields. That's why they're coming up.
Okay.
You don't put them together like you expect. Well, depends what you expect, but you don't put them together in the obvious way to make the normal integral, right? Meaning this plus this is not the same as that.
Okay, that's what I was under.
This plus this not equal to that.
Okay.
Okay. Don't think that they are related, but that is not an equality.
All right.
Okay. If I was on the board, I would write this equality and then put not equal sign and circle it in red with a big frowny face and say not equal. Don't do this.
Aren't they equal?
They are not equal. Okay. So let's think about doing this in a more systematic way, okay? Because I'm getting kind of tired of this stuff here, x of t and y of t. If I want to do this in higher dimensions, I'd have x of t, y of t, z of t. And even higher than that, x of t, y of t, z of t, w of t. That's a lot of effort, right? So that says we should vectorize this notation and vectorize these ideas for more concise description of our objects, right? I gotta put my numbers here. So vectorize things. So if I am integrating ds, I can describe my parameterization as some function, a vector valued function, right? As a vector. Not a vector, but it is vector valued, but, and parameterization x of t, y of t. I could describe this as an r of t, right? Now this is a vector, just like we did before, right? And so now the integral ds, this is the same as the integral of f evaluated at r of t, right? Times, what is this thing up here? This right here is the length of the derivative of r of t.
Magnitude.
Yeah, the length of the magnitude. Okay, well, the length of the derivative. Length and magnitude are the same word here, right? The length of the derivative vector. So if you take the derivative of this, what do you get? You get x prime of t, y prime of t, which is still a vector. And you take its magnitude, which is this. So this is r prime of t dt. Okay, so we have a concise way of writing this in vector notation, allowing us to move line integrals into higher dimensions easily, okay?
And this is because you've moved into parameterization, correct? It's not that you went to polar coordinates.
No, I didn't move to polar coordinates. And I was already doing a parameterization. All I just did was vectorize my parameterization. I just wrote it in some vector notation. That's it. Nothing different, nothing new.
No, it's just that it's so similar. That's why.
Yeah.
Clarify that.
Okay. Okay. Does this make sense? And also, now imagine doing this in higher dimensions, right? I can have z's here now. And all the formulas work exactly the same, okay? So my lines, my curves can be in 3 space now as opposed to in 2 space, okay? So now, why do we care about these things? Yesterday, Tuesday, I said we're gonna talk about some applications of line integrals. So one very, very obvious application that we can think of off the top of my head is mass. Let's say I have a wire in 3 space, right? And it has varying density across the wire. That may happen because the wire is hotter or cooler, right? Heat can change the density of an object. If it's warmer, it expands. If it's cooler, it contracts. So its density could change on a local level. And I want to know the mass of this object that is essentially this line integral. Okay? Another thing that we could be interested in is the work done by some exterior force on an object that travels through that curve. Okay? There are a couple other examples like Ampere's law and Faraday's law, but those are really examples of Green's theorem, which is another application of line integrals. So we'll talk about Ampere's law and Faraday's law when we talk about Green's theorem. I can't see that, but, and I can't hear you either.
Ampere's law.
Yeah, Ampere's law and Faraday's law. They do use line integrals, but they use line integrals because they use Green's theorem. Green's theorem we use as line integral. So we'll talk about Ampere's law and Faraday's law and Maxwell's equations after Green's theorem. Maxwell's equations will come after the divergence theorem, divergence and curl. But so those two things use line integrals, but only because Green's theorem uses line integrals. Okay. Any questions? So if you are interested in physics or engineering of some sort, you will need to know all about those laws, and they're essentially applications of Green's theorem and the divergence theorem, which are both applications of Stokes' theorem. Okay, so why did we go about this? I want to talk about, let's do a quick example before we get too far ahead of ourselves. Okay, so I'm going to look at something nice and easy. The integral of c y, that's too long. How about yx ds, where c is the curve given here. Let's try to draw this. It's 1. Okay, so it's just a circular helix that goes up. And this is, this goes to pi. Okay. So how do we deal with this? What do we do first? We parameterize, yes. What parameterization are we going to use? We'll write this in vector notation so we get used to this. How do I parameterize this helix?
Is it like sine t, cosine t, and t?
Yeah, close. I'm going this way, counterclockwise, right? So I should have cosine t. That's the way the unit circle goes.
Sorry.
Cosine t, sine t, that makes the circular motion, and then t makes me move up.
Yeah.
Okay, good. What's r prime of t?
Negative sine t, cosine t, and 1.
Yep, not extremely difficult here. Can you explain that? Explain which one, Maggie? R of t. So how do I parameterize this circle? The unit circle is parameterized, or can be parameterized, as cosine of t, sine of t, right? We talked about that. That's the only parameterization you really, really need to remember, right? So if I were sitting on top of this thing, this helix, and looking straight down, I would see just a circle, right? Imagine collapsing this slinky down, I get just a circle. That looks like this, and this is its parameterization. So now, when I want to lift up the circle and stretch out the slinky, all I need to do is add a z component that's not 0, right? If I flatten this thing down, I would just get the z component is always 0. So if I'm going to stretch it out, I just need to give the z some height. And that's what this does. As t gets large, we move up. We need some parameters on, yeah, this is z here. This is x of t, y of t, z of t. So we need some parameters on t. What does t go from?
0 to 2 pi.
0 to 2 pi. Okay, so we can compute this. How would we, let's set up the integral. We're not actually going to compute it because that sounds horrible. But integral yx ds, this is the integral from
0 to 2 pi.
0 to 2 pi of what goes in here now?
Sine of t, cosine of t. Oh,
Sine of t, cosine of t. Times the length of the derivative, which is this thing, which is sine squared t plus cosine squared t plus 1 dt. Right? And so this should be integral from 0 to 2 pi of sine t cosine t times root 2 dt. I don't know what this integral is, but I have a suspicion it's 0.
Why 0?
I will verify. I always forget these ones, but
It's u du.
2 pi, that's pi. This is 2 pi. Okay, so why do I think this is 0?
Oh, is it because it
What does this integral represent? I covered it up, but
the
this is the
temperature-
integral of this function. This function looks like this, 0 to 2 pi. This cancels out that, and this cancels out that. Integral should be 0. We can compute it if you like, but I'm pretty sure it's 0. Okay, I think if you just did a u substitution, you'd also get 0. Okay. So we shouldn't forget our basic calculus stuff. Coffee got cold. That was very convenient. That actually worked out well. Okay. So now let's compute this just to say we did. Integral of c f of xy equals x f of x y z is equal to yx f of x y z dx plus f of x y z dy plus f of x y z dz. Okay. So what do we get? In this case, it might be the same. No. Okay. So that's going to be annoying to compute. But what is this? Let's understand what this means. That means we make a parameterization of all these parameters, all these functions, x, y, and z, parameterize them in some common variable t, and then add those integrals up, right? I have a parameterization already, right up here. That's awesome. I can just go and essentially follow the directions, right? So this says I need to evaluate my function at that spot, cosine of t sine t, times the derivative with respect to x, right? Which is that, minus sine t dt, 0 to 2 pi, plus cosine t sine t, cosine of t dt, plus cosine t sine t 1 dt. We can factor all the dt's and the cosine t sine t. So we should get integral 0 to 2 pi of cosine t sine t times cosine t minus sine t plus 1 dt. And I don't think this number is 0. But we could compute this quickly because I'm curious what this number is. Right. Oh, come on. Come on, stop. Integrate cosine of t sine t times cosine of t minus sine of t plus 1 with respect to t 0 to 2 pi. Oh, it is equal 0. That's unfortunate. So in this case, they are the same. That was very convenient.
Excuse me, I'm not quite sure what we just did there. I thought you were doing the second procedure just as a check on the first procedure. Is it supposed to give a different answer than normally?
It doesn't always give the same answer. So what I was saying was, back to this discussion, integral ds is not always equal to the integral okay? They are not the same number all the time. We got lucky because we got some cosines and sines and they multiply and they got 0. Okay? So be very, very wary of this. This is not an equality all the time. In some cases it is. And I think in this case it was because it's a nice function. Okay?
Might it have to do with symmetrical functions?
It has to do with something called, what is the word they call it? A conservative field. So it's related to the gradient. Okay. So let's move on here. Now let's talk about line integrals over vector fields. So that's really the reason that we were interested in talking about line integrals. Well, a reason. Vector fields. So imagine a very reasonable situation. I have some magnetic field, right? And I want to see how much work is being done. Or I have some force field, not like force field in the blocking stuff sense, but a field that describes forces at any given point, right? And I want to add the work done by that field up, right? So we'll start with that example, work. Recall, work is equal to force dot the displacement vector, right? So I have some curve in 3 space or 2 space. I can do 2 space too. Like that, and I have some vector field going on here. I don't want to draw all this stuff in here to make the picture really ugly. Okay. So then if I'm right here, let's say my vector field varies, obviously, and my displacement vector also varies, right? My displacement vector is not always pointing in the same direction, and my vector field may be stronger here or weaker here, right? So I want to compute the work done. And I can do that by separating this curve up into small little chunks. I'll call them P's. I call them S's. I should probably call them S's. I separate them along the length. And how do I compute the work? I need to have a force vector and a displacement vector, right? So if I have some if I separate this into small pieces, I have a displacement vector. It's that vector, the vector that is tangent to the curve, correct? Describes the displacement. So we had a special name for this, T, capital T. Right, this is the unit tangent vector at the point x, y, z. Is the unit tangent vector at x, y, z. Question? So we've got a tangent vector that describes displacement. Now we need a force vector. What force vector should we use? That's not a trick question. What is the force vector that's acting on this object, this particle?
Is it the vector field?
The vector field, right? This is my displacement, d. My f is f of x, y, z, right? Not extremely sophisticated. So how do I determine the work being done on this small bit right here? The work on that small interval is F on that interval dot T. F at the beginning and T. So we pick a point, we have x, y, z, we take the force vector and dot it with the displacement vector, which is our tangent vector, right? So
Got another vector, right?
what is the dot product of two vectors?
No, it's a scalar. Right?
It's a scalar, yeah. So now we've got, this is the work being done on this small bit. What should we do next? What do we do? What do we always do? We add them all up. So the work done in total is the sum of dot right? So why do we need this ds here? Because this is really, t is a unit vector in the direction I'm going, right? And ds tells me how far I'm going. So t times ds actually gives me my displacement vector.
I thought the tangent vector described
So-
displacement.
Tangent vector, this unit tangent vector describes the direction I move, right? And ds describes how far I'm moving.
Oh, so the
So their
Cross.
product describes displacement.
displacement. Okay. Ah, all right.
Right? Does that make sense? Right? The tangent vector only describes direction. It's a unit tangent vector. So we need delta s to describe how far we go. So then we add this up, we take a limit, and we get an integral. Integral of f dot, with my curve, t ds. This is the work that's being done, okay? Any questions? Nope. Okay.
Those two vectors will not be orthogonal to each other, will they? Just because that's the notation we used earlier for two orthogonals, if you recall.
What notation?
The f versus t. Remember when we did orthogonal vectors and we determined a t vector, and then we
Well, when we did the tangent vector, we had the n, which is the normal vector, and the binormal vector. So we had n's and b's.
I think there was another that was orthogonal to. Okay, I thought there was a third one that was orthogonal to.
Yeah, there are three of them: the tangent vector, the normal vector, and the binormal vector.
Oh, great. So there was no f. I misremembered.
Yeah.
Thanks.
And this could be orthogonal at some point. That's not to say they can't be orthogonal. Okay. There could be orthogonality happening. Any questions about the equation? So let's look at this in a little more detail. So if we have this work integral, W, this is f dot t ds. Well, t is the derivative divided by the length of the derivative. Right? That's what the tangent vector is, where r is a parameterization of c. Right? So if we look back to our vector equation, we can make a substitution and say that, well, W is the integral of, I'm going to make this substitution here. So f at r dot, this is just a simple substitution, nothing special. And then I multiply by the derivative, the length of the derivative. This substitution here comes from the definition of this line integral we had, right? How do we compute the line integral? We take the function, we evaluate it at the r, the vector, and then multiply by the length of the derivative. In this case, our function is this entire function right here. Okay? And that worked out really nicely because we get work is integral dt. These r's cancel. There's a prime there. dt. Okay? So to compute the work, all we got to do is take the function, evaluate our vector field on our curve, and then multiply by the derivative, and then integrate. Okay. Any questions about that?
Did you go back one paper? Or like, yeah, thank you.
We good here?
Yeah, sorry, I just wanted to check something. Thank you.
So, okay, we've got work. We have a way to compute work with respect to a parameterization. And we're going to make a slight abbreviation change. Okay? So, think of this here. This is the derivative of r, essentially. So if r given r of t, dr, right? This should be, as a vector now, should be r prime of t dt, right? So we can make a change of variables to express this in a pretty common way. Change variables. And we write work is equal to the integral across the curve of f. This is this vector, this part, dot dt, dr, sorry. Okay. Does that make sense? All we've done is essentially change variables. So the work can be described like that. It can be described like this. Or it can be described like this. This is a very common description of work. Integral f dot dr. Any questions? No? Let's do some examples. Okay. So let's look at this example. Let's find a nice problem. So let's say f of xy, this is equal to xy squared I minus x squared j. R is given by t cubed I plus t squared j. 0 less than or equal to t less than or equal to 1. Evaluate integral f dr. Okay. So go ahead and evaluate that, and we will check in a little bit. Go for it. Get some water. Okay, let's start here. Start with someone who's been quiet all day. Darius, starting from the bottom now.
Yeah.
How do we start this problem?
So you first need to parameterize it. So you get your R of t and then your dr.
Okay, do we need to parameterize here?
Actually, no, you don't.
We
just
already have a
dr.
parameterization. It's right there.
Yeah. So you make dr
Okay, what's dr?
3t squared I plus 7t to the 6j.
T to the 6. That's a 2. Just bad at writing stuff.
Oh, I'm sorry.
Yeah.
So 2t.
2t j dt. That's
Mhm.
good. So let's move up in the line. The list keeps changing. So it says, Yosin, you're next. What should this integral say?
What should it? You should write f of in terms of r.
Well, let's start from the left. What are the bounds of my integral?
Oh, 0 to 1.
0 to 1. So tell me exactly what to write here. You don't have to tell me what it means. Just what symbol should I put on the page?
Good one.
Maybe a hand, somebody else? Maggie, if you're still here, I'm having trouble with the connection. Okay. Like the network connection or connecting this math together? The Wi-Fi. Okay. Can't fix that one. Okay. So we need to evaluate our function. So we got the first part. Well, we got the second part. That's r prime t, which is 3t squared I plus 2tj dt. So we need to get this f part, right? And like Yosin said, we need to evaluate the function f on this curve, right? How do we do that? This has x's and y's in it, and this doesn't have any x's and y's in it. So what do I put in here? What do these things mean?
Well, t cubed would be equal to x, and t squared would be equal to y.
Yeah, remember, r of t is x of t, y of t, right? We're writing it in this ij notation, but it can also equally be expressed like this. Oh. Right? So what should go here?
So you just put in t cubed
T cubed
plus t squared,
plus,
or I guess that's plus.
well, so x of t is t cubed, and y of t is t squared. So this should say t cubed
Oh, times t squared.
times t squared squared, right? I
Minus t cubed j.
minus t cubed squared j, right? Dot product. And now this is, these are two vectors, and we got to dot them together, right? What's this dot product?
Wait, I have a question.
Yep.
Don't we? I thought we divided our we took our r prime of t. Don't we need to
Yep.
find the magnitude of that and then divide it by?
Nope, we don't need the magnitude at all. That it happened to work out real nice that we had the magnitude here, but it got canceled by the other
It
magnitude.
gets canceled.
So
Okay.
this is all we need to compute here.
Can you explain the whole like f process again? Like I don't really get it.
Okay, so let's think about what happened here. R of t is written in this format, right?
Mhm.
But this actually means this, or they mean the same thing, right? So that says that x of t is t cubed and y of t is t
okay.
squared, right?
Yeah.
Because this is the j component is t squared. So that means the j component is the y component.
Mhm.
That's t
Okay,
squared.
now I understand. Yeah.
And so now everywhere I see an x, I put a t cubed. Everywhere I see a y, I put a t squared.
Okay.
And that's what we get here. Okay?
Yeah.
So now that we've, any more questions on that? That is admittedly a confusing situation here. Now, we're gonna go and take this dot product, right? I'll write this in a nice, in more compact. 3 plus 4 is 7. T to the 7th I minus t to the 6th j times, or dot, 3t squared I plus 2tj dt. So what should I get here now once I take the dot product? How do I take the dot product? Got to remember all of our vector calculus at the beginning.
Yeah, take the like product, so I and J's and K's go together.
Yep. I's go together, J's go together, and K's go together. There's no K's here. So tell me what to write here, Darius.
So you got, I'm sorry, that's my dog.
Okay. Someone else here. Tell me what to write here. Dog wasn't happy about that, I guess.
Let the dog answer it. I'd say 3t to the 9th I.
3t to the 9th I.
And look how nicely it works out. Is that a 3 you've got here? After
Here?
the other one? So that's another t to the 9th. Minus 2t to the 9th?
This is a t to the 9th? I don't think so. This is a t to the 7th.
Okay, I couldn't read it.
Yeah. Yeah.
T to the
Minus
t.
2t to the 7th. J. Oh, wait. There's no I there.
That's supposed to be a 1?
What?
Okay, yeah, it's just a 1. So why has it got that?
Why does it have what?
Well, you've got a power of, it's your J hat.
Where?
Your J is just, sorry, illegible.
Oh, sorry. All right, right here?
Yeah, T6 is fine, but then 2T,
Oh, this is an arrow
okay.
on top of my J. I'm just
All right.
scribbling. Right, so I have a dot product. This should be a number, right?
Yeah, is it like 3t squared times t to the 7th?
Yep, we're just taking a dot product. How do I take a dot product? I take the components that are the same, I multiply them together, and I add up all the components.
Yeah.
Right? This times this, plus this times this.
So
dt.
3t to the
9.
9th. Yeah, okay.
And then we integrate this, okay? We can integrate that. That's a polynomial function. Not super hard, okay? But I'll leave it there because that's a lot of effort.
So what exactly did we find? I feel like I don't really understand what we've done though.
Okay, so let's take a step back. That's a good question. Well, let's answer that in just a moment. We're gonna go finish where we're at. We can compute this integral. It's pretty easy. It's 3/10 minus 2/8. Okay, so well, whatever number that is, we wanted to compute it just because it would give us some sense of, what's this, 0.3 minus 0.25, 0.05. So that's 1/20th. Okay, good. So what does this do? What does this mean? Okay, so what this means is if I had a force field given by this and its curve R, this integral is evaluating the work done by the force, the field on the curve R.
So this relates back into when we talked about dropping like a stick into a river and that being a vector field.
Yes.
And we move from point A to point B. That's
Yes.
So our parameter, or our parameter t being bound by 0 to 1, that's moving from point 0 to point 1.
No. That's moving from time 0 to time 1, right?
Okay.
Imagine I drop the stick in, that's time 0.
Time 0.
And then whenever it arrives at the end where someone picks it up, that's time 1,
Okay.
right? R of t describes location, t describes time.
And then our vector field is described by f.
Yes, our vector field is described by f. In the context of this river example, that's the flow of the river at a particular point, right? And as we said, it could change depending on where we're at, right? Maybe there's rocks, maybe some spots are deeper or shallower and they move faster or slower. maybe there's eddies. So this can be thought of as the work done by the river on that stick.
And the direction or the path that the stick travels is R.
Is R. Yes. Okay.
That's really cool. I like that.
Any questions? I'm gonna be first to admit this is like a somewhat sophisticated setup. I mean, it is. We described a very complicated thing, right? We're measuring the work exerted on this twig as the river carries it downstream, right? That is a difficult thing to quantify. And so this is how we're quantifying it. So when you're going through these examples, be really, really careful about what you're actually doing, right? And make sure that you're integrating a scalar, right, after you take a dot product, okay? So at all these steps, check your units in the sense of what kind of object I'm integrating, not necessarily units as in unit of measurement, because we aren't actually measuring things necessarily, okay? There's one more thing to discuss, and it goes back to why we were talking about X's and Y's and Z's to start with, okay? So I want to relate the integral of a vector field to the integral of scalar fields, right, which we talked about at the beginning. So the integral of the line integral of a vector field and line integrals of scalar fields. Okay, so let's write my vector field F. This is P, that's not a vector, it's a scalar, I plus QJ plus, what letter did I like to use? R, PQR. Okay, sorry. So this is now a vector, right? And each of these P, Q, and R are functions of X, Y, and Z. Are functions of X, Y, Z, normal functions, right? Their output is one thing, scalar functions. So I would really like to relate this to something with these things in it, right? That seems reasonable. And so how do I do that? Well, this is equal to PI plus QJ plus RK dr, which is X prime of T I plus Y prime of TJ plus Z prime of TK dt. I just fill in the equation. Right. If you can't read at any point in time, please tell me. Okay. So now, what is this equal to? Let's take the dot product, right? That says this is the integral of P times X of T plus Q times Y prime of T plus R times Z prime of T dt, right? What is this here? This is we got to really kind of expand this to be clear what we're doing here. This is P of R of t times x prime of t, right? Because we need to make sure that we're evaluating our function on our curve. So what does this tell us? What is this integral right here?
Wait, isn't that taking it with respect to the x axis?
Yeah, exactly. This
The
is the
derivative?
integral P dx,
Yeah.
right? And this is the integral of Q dy and the integral of R dz. Okay? So what does this tell us? This says the work, as we expect, can be broken up into work done in each scalar direction. P dx plus Q dy plus R dz.
You go down a little. Thank you.
Okay? So if I have a vector field and it's doing a bunch of work, I can compute the work, overall work, done by computing the work done in each direction and adding them up. Okay? Does that make sense? This is a special case. Well, what I said before is if you separate them into x and y's and add them up, you don't get the arc length, right? But in this case, if you choose the right functions and separate them in x and y's and add them up, you get the work. It was essential that I picked these functions with respect to each variable, right? Because this computes the work done in the x direction, essentially, the y direction, and the z direction. And adding them all up gives me the total work.
So before you go any further down the page, the thing that made you able to add them up is because they are related to time.
Yes,
Correct?
they're all parameterized by the same variable t. Okay? That's the only way this integral means anything. Okay? Back at the beginning of this discussion.
Could we do the same thing with arc length?
So this is essentially an arc length integral, right? Because when we built this up, we're imagining traveling along the curve. Right?
Yeah, you're right.
And that is arc length. So think of this as this side of the equation is I'm on the stick that's riding down the river, right? Think of this as I have some grid access and I have some coordinate system where I place the river and the point of the stick is at some XYZ coordinate in my coordinate system, right?
Mhm.
And these are done in computations in my coordinate system. And this is me on the stick.
Yeah, okay.
Right?
I guess I was thinking, so I remember you saying that the integral over a curve C of some function parameterized to t dx and then dy was not equal to the arc length.
Yes.
And
It is not the same, but that's
Not
not
the
what
same.
happened here, right?
yeah, it's not, yeah.
So in our one example that I computed things, I picked a shitty example and they came out to be the wrong number, the same number. That was not representative of what actually happens. if we want them to be equal here, we need a vector field first to always be equal. We need a vector field, and we need to separate the vector field into its appropriate components, integrate those components appropriately. Our example previously was one I just made up, and it worked out randomly nice, but it did not illustrate my point, unfortunately. Okay. Does that make sense? So let's go and compute the previous example we just did. And I'm going to write it again here, so we don't forget. F and I want to evaluate this. We just computed this, we got 1/20th. So now let's compute it separately, right? From our previous equation, we know that this is equal to the integral of p dx plus q dy. What is p and q here? What are p and q here? What is p?
Just the x portion?
Yeah, which is?
X, y squared?
Yep, so p of xy is xy squared, and q of xy is minus, you have a minus sign, x squared, right?
Wait, don't we incorporate r of t into this?
Well, we're not quite there yet. We're just finding out what p and q are,
Okay, never mind, sorry.
right? And I want to compute this now. So if I want to compute this, I need to incorporate r of t. And so this integral from 0 to 1 of p of r of t. What is p of r of t?
You put r into p.
Yep. And what do I get?
T to the 6th? Oh no, t cubed y squared?
Okay, t cubed times t squared. What is x and y here? X of t is t cubed. Y of t is t squared. So p of r of t is t cubed t squared squared. Dx, what is dx? X prime, what is x prime?
3t squared?
3t squared. dt. And now I'm going to do this part. So q of r of t is what? Minus t cubed squared times y prime, which is 2t dt. And if we compute this, we get essentially this number right here. We get this exact same integral. And so we'll get the same number.
Professor, with all due respect, I'm tempted to say, so what? It's the same operation as we did before. We were just doing it as vectors before, and now we've broken it up into two integrals, right?
Well, yeah. When you get an equality, that's fine. We get the same number. We get the same answer. computationally speaking, they're not much different. The one difference I have to do is I take a dot product here, right? I need a dot product here. And here I take no dot products, right? But the purpose of this equation is to say that the importance of such an equation is to say, independent of what reference point I'm in, I can still make this computation and it's still the same, right? So in practice for us, we're only gonna need one of them because we're gonna compute in whatever reference frame I have, right? Often the second one, this thing, is easier because just think about how we organize things. We have some coordinate system that measures length and distance, right? It's usually extrinsic to the object itself.
I get it. And sometimes you may be able to measure one thing, but you can't measure another.
Exactly.
Yeah.
So the idea that we can measure, we can compute this from whatever we get, and it'll be the same answer is the important part. In this case, the example was trivial because we had both things. We wouldn't really need to do both things. Okay. Does that make sense? So we'll end a little early today, but I want to say, please, please, please look at parameterization. I don't know how many times I've said that today, at least 3, but actually look at parameterization and look back at chapter 13 and 12 to remember all your vector stuff. Because that will be necessary when we talk about, what do we talk about next? Next, we're going to talk about the fundamental theorem of line integrals, which is essentially the fundamental theorem of calculus for line integrals. We'll use that to talk about Green's theorem, which we'll talk about line integrals in surfaces in open space. And Ampere's law and Faraday's laws are results of Green's theorem. And then we'll talk about divergence and curl. We'll talk about Stokes' theorem, which is the generalization of all of these theorems. And then an application of Stokes' theorem called the divergence theorem, which will be fundamental in Maxwell's equations. Right. So to do that, I'm going to reemphasize this. You need to be good at parameterizing shit. Second, you need to know how vector operations work well. You got to get your dot products back in order. You got to get your cross products back in order. You got to know all of these things. Okay. So that was forever ago, but we will need them all now. Okay. So if you were going to do anything this weekend, math related, and you don't already remember all those things, go back and look at them. Any questions? No? Okay, seems good. Have a nice day. I'll see you Tuesday, virtually.
Bye-bye.
Bye.